In the kindergarten story, the turtle might have won the race because the rabbit rested and the turtle was slow and steady. But in Air Force, rabbit would be a better suited professional since it could rest, recuperate, and thereafter run with full josh, like so. Or we can say that the rabbit was able to do speed adjustment. We all know the relation between distance, speed, and time. For the scope of today's lecture, we shall limit ourselves with only two variables and assume the distance to be constant. Hence, we are left with speed and time. Any timing action would be a direct result of speed adjustment. In the civil scenario, it could be required to reach early if you want to save fuel, or to reach late if there is traffic at the destination or some other restriction. But since you are a military aviator, timing action becomes even more relevant for you, as you might want to reach early to surprise the enemy, or you might want to reach late after the enemy has exhausted his defenses. So let's start with the basics of speed adjustment. As we know that the distance has been assumed to be constant, so we can say that the old speed and old time will be equal to the new speed into new time. Subsequently, these will be referred to as SO, TO, SN, and TN respectively. Another corollary to the basic formula states that if the speed of the aircraft is changed by ground speed per minute, then 1 second is gained or lost for every minute of flight. Let us see how. Assuming the basic speed of an aircraft as SO knots, as per the corollary, the speed change should be equal to ground speed per minute, which in this case will be SO by 60. So the new speed becomes SO plus SO by 60. Also, this new speed has to be held for 1 minute, which is 1 by 60 hours. Putting these values into the basic formula, we get SO into TO is equal to SO plus SO by 60 into new time, which is 1 by 60, which also gives us the value of TO as 61 seconds. Thus, for an old time of 61 seconds, if the speed is increased by ground speed per minute, the new time comes out to be 60 seconds. Hence, 1 second is gained in 1 minute. Now, even this corollary of basic formula can also be cumbersome in some cases, as the ground speed of the aircraft may not always be divisible by 60. So what we do is take a convenient round figure of speed change, in most cases at 10 knots, and calculate the time gained or lost with reference to the distance to go. This rate would vary with the basic speed for obvious reasons. Now, as we have a simplified rate of change of time gained or lost with reference to the distance, we can post it on the map. Hence the name rate posting. A statement for rate posting of Avro would be an increase and decrease of speed by 10 knots will cause a gain or loss of time in seconds equal to the distance to go in nautical miles. Not convinced? Well, here is the derivation. Taking the basic speed of Avro as 180 knots, if we increase speed by 3 knots, which is the ground speed per minute, as per the basic formula, we would be gaining 1 second in 1 minute. Similarly, if we increase the speed by 10 knots, which is 3.3 times the basic ground speed, time gained would be 3.3 seconds in 1 minute by ratio and proportion. Now the new ground speed is 190 knots, so the distance covered in 1 minute of flight will be equal to 3.2 nautical miles. Also, in 1 minute, time gained is 3.3 seconds and distance traveled is 3.2 nautical miles. So we can safely conclude that gain per nautical mile will be equal to 1.03 or almost equal to 1 second per nautical mile. Hence, an increase of 10 knots in ground speed results in a time gain equal to distance to go. So if you are 90 nautical miles short of destination and you increase your speed by 25 knots, how much will you gain? By rate posting, had you increased your speed by 10 knots, you would have gained time equal to distance to go, that is 90 seconds. But since the speed increase is 25 knots, you will gain time 2.5 times 90, which is equal to 225 seconds. Although rate posting is a simplified ready reckoner, it is not very accurate formula. Also, if you go into the detailed calculation, you will discover that the net effect of time gain by increasing the speed by 10 knots will not be exactly same as time lost if you decrease the speed by same amount, that is 10 knots. Since you are a military aviator, you might be flying a tactical routing and might not be sure of the distance to go. Then how do we do timing action? Well, Bell's method to the rescue. Bell's method states that increasing or decreasing speed by an amount in knots equal to seconds late or early and holding it for number of minutes equal to the basic ground speed per minute will cater for the timing error. Don't believe me until I prove it. Assuming the ground speed of an aircraft is a knots and it is late by x seconds, so by Bell's method the amount of speed change should be equal to x knots. Hence, the ground speed should be a plus x. Also, the amount of time the new speed has to be held should be equal to the basic ground speed, which is nothing but a by 60 minutes. Now, all we have to prove is that x seconds are gained after a by 60 minutes. As the new ground speed is a plus x nautical miles per hour, it can also be stated as a plus x by 60 nautical mile per minute. Also, the distance covered with this new speed will be equal to the new speed into new time. This value of d will be constant even if we fly with the old speed. Hence, the old time can be calculated as d by a hours or d by a into 60 minutes. Substituting the value of d from above, we get old time as a plus x by 60 minutes, and the difference of old time and new time will be the time gained, which comes out to be x by 60 minutes or x seconds, which was exactly what we wanted. Let us solve an example. Consider an aircraft with a ground speed of 240 knots. So its ground speed per minute comes out to be 4 knots and it is late at a checkpoint by 20 seconds. By Bell's method, you would like to increase the speed by 20 knots. So the new speed would become 240 plus 20, which is 260 knots. Also, you have to hold this speed for a time equal in minutes to the basic ground speed per minute. That is to say, you have to increase the speed to 260 knots and hold it for 4 minutes. What happens when you are late by 1 minute? Then by Bell's method, you have to increase speed by 60 knots, which might not always be possible. Similarly, if you are early by a minute, it would ask you to reduce by 60 knots, hence your new speed might be close to or even below the minimum clean. This is one of the limitations of Bell's method, that it asks you to breach the aircraft performance envelope. So the need arises for a method wherein the speed change will not be dictated by the time early or late, but will solely be dependent on the original ground speed of the aircraft. Hence came the rule of N, which is a generic method stating that increase or decrease speed by n times the ground speed per minute and hold it for number of minutes equal to 1 by n times the number of seconds early or late. So if your ground speed is a knots and you're late by t seconds, then by the rule of n, you increase your speed by n times your ground speed per minute and hold it for 1 by n times time late. Now, similar to the Bell's method, you find out total distance traveled, which will be the product of new speed and new time. And again, similar to the Bell's method, you find out the old time by dividing this distance by old speed. Substituting the value of d will give you the old time, and the difference of the two timings will give you the total time gained. In this case, as you put the values, you get the time gain as t by 60 minutes or t seconds, which proves the viability of rule of n. Point to note is that n could be any positive whole number. It could be 3, 5, or any convenient number, and thereafter could be called as rule of 3, rule of 5, and so on. So let's quickly do a few questions. Assuming the basic ground speed of an aircraft as 180 knots on a low-level mission, it finds out that on the first checkpoint it is late by 18 seconds. By the rule of n, find out the speed change and the time to hold. As we know, the speed of the aircraft is 180 knots, so the basic ground speed becomes 3 knots per minute. Now applying the rule of 3, we find out that the increase in speed will be 3 times the basic ground speed, that is 9 knots, and time to hold will be 1 by 3 of the time early or late, which comes out to be 6 minutes. And for the same basic ground speed of 180 knots, if you find out that you are 45 seconds late and you have a restriction of maximum speed change permitted to 30 knots, you can apply the rule of 5 and find out the speed change required as 15 knots and time to hold would be 9 minutes. Now all these methods assume that the timing change is only due to the external factors and the aircraft is flying a ground speed same as that planned on ground, which is hardly the case. Thus, factor X comes into play. It caters for the variation of actual ground speed and the flight plan ground speed. Factor X is given with the formula X equal to ground speed per minute into seconds late or early divided by the time actually gone in minutes. To prove it, we go back to the basic definition of factor X, as it is the deviation of actual ground speed from the flight plan ground speed. We can say that it is the difference of new speed and old speed. As x is the difference of speeds, we can say that the new speed Sn is equal to So plus x. Putting the values in the basic formula and solving it for x, we get factor x is equal to old speed into the time difference upon the new time, which is nothing but the time lapsed. Since the time lapsed will be in minutes, we can say that the factor x will be defined by ground speed per minute into the time late or early divided by the time gone in minutes. Remember that factor x is to be applied over and above the correction determined by the previously discussed timing action methods. So to summarize, we first studied about the basic formula and its corollary leading to rate postings, which was a bit cumbersome, so we studied the Bell's method, wherein the speed change was governed by the time early or late, and it was leading to exceeding the performance envelope of the aircraft. Hence, we studied the rule of n, where the speed change was dictated by the original speed of the aircraft. And finally, we studied the factor x, which was to be added over and above the speed changes calculated earlier. With this, we finished the timing action by speed adjustments. Do practice a few numericals based on each method. Thank you and happy landings.